Hello, this is the second lecture on the courses of Nonlinear Polymer Rheology. I will describe a variety of topics as listed here, a different subject showing up in different times indicated here.
Any questions? Okay, so we will formally start and continue along the line of introduction. I realized if this is going to be captured on screen, I may as well just each time showing my electronic book. This way, everything will be very clean. Everyone will see absolutely the same thing. So there won't be even need for that poor copy of the book. Now, one more thing to mention. I know only a few had my course on polymer physics. I think it will be, so everything will be more or less self-contained, but I think for those who didn't have Maxwell model, for example, discussed in some form, I will try, because my polymer physics was recorded. So I should be able to get that video uploaded to the Brightspace so that you guys, if needed, can view that recorded lecture on Maxwell model or things like that. But of course, the Maxwell model is explicitly described in just a couple pages in the book as well. So it's either way, we won't go anywhere without self-containedness. Okay. So we start as usual. We start from the most elementary parts, and of course, I will point out each time. Where is Chaitanya? Well, I will point out each time when something elementary may have something hidden there, right? As we last time started to talk about. So I will mostly follow the book, but I will not be as detailed for the first 5 chapters. So the first 5 chapters will all be under the title of Introduction. And then chapter 6 is where we start to heavily tackle a leading aspect of polymer rheology, where I swear that you folks did not learn much from your polymer rheology course. I presume. So, but that will be a stepstone for everything. So let's be very thorough here. I will use this format. This is instead of PowerPoint. It's called Window Journal, and for those who are using Mac, any of you using Mac? So otherwise, this thing is directly readable from PC. But otherwise, I can convert it into a PDF, and then of course anyone can read it. Okay, so I copied this from PowerPoint to this so-called Windows Journal. And let's begin. So we will I will even repeat some of the things. I really have a habit of trying to save time and verbalize a lot and not writing much. And this could become a difficulty for some of you who, especially through a mask, who couldn't hear me well. Okay, so let me just be formal. So we are, let's say this is our introduction, and we can break this introduction into different sections. And one can start with the definition, right? About I want to repeat this anyway because I want you to appreciate rheology, right? It's a science. As I said, this is the core mission of rheology, not the tool. Oh, come on. I see what I'm doing. Only the mouse will react this part, I think. Oh, come on. Delete. Not the first time. So what is the... Oh, God, it gets so fancy. See that there is an icon there. It looks like only the mouse is controlling all these things, and the pen is always it's always responding to it. Look like okay, it's just something for me to figure out. So it's a science on deformation of materials, right? That's very formal, so I write it down. And remember, this is a core mission. This is not the so-called rheology as a characterization tool. This is it has a science part of it. And speaking of, you can see it's really annoying. Speaking of this being deformation, oops. I see it's, this pen is just a pen for the touch screen. It's not even responding to that won't be right. It's not even responding to the color of this. I never had trouble last time I did this. Last semester. So. Yeah, you have to change the color here. That's, yes, it's fine. But it's. I'm sorry for the struggle here. So now it's red. In any case, it's about deforming. It's about shape changing because all the processing involves shape changing, and certainly all the application of your material may involve whether your material is able to resist shape changing or not. When you deal with the shape changing, there are really two components to it, right? They're really a matter of, just like in the case of shear, there's a matter of, last time we talked about whether the shear is going to obey homogeneous deformation or not. Like my plane moves, then half height move halfway. So that's the strength field. And as I said, it usually is assumed to be subscribable. In other words, you can subscribe that field. And what's left is for you just to determine the stress field or stress. So that's the traditional view of rheology. So this task was assumed to be simplifiable to dealing with this because this is already known. That's how I learned all along about rheology. I'm sure when you guys learn rheology in traditional format, this may not even be emphasized, honestly. Meaning emphasizing it in a conscious way, saying, hey, the strength field is given. Let's just deal with what's the stress response. Of course, yes, of course. Right. No, I'm sure you describe both, but what I mean, what I mean is you may not explicitly emphasize that the task usually is not a task where you need to determine the strength field. Strength field is, as I described in shear, will V over H. It's done. You don't talk about it anymore. You don't even go ahead and verify that's true or not. So in that sense, let me be clear. What I really mean is, in a traditional way of teaching rheology, this was not explicitly discussed. It was just introduced as if this must be true. So I'm just bringing it down by saying, when this is not true, you have a double job. You need to determine both the strength field and the stress field. And of course, furthermore, you quickly should recognize that the shape change can also be achieved by not imposing how much you are changing its shape, but rather by imposing a force. In other words, become force controlled. So I'm sure that you have been discussing. There are two modes, and I will come back and forth about it. There are really two modes. The two modes are really different. And if you, I wish you'd spend a moment to appreciate it. In the first mode that I introduced last lecture, you move your upper plate with a velocity v, sort of controlling the rate at which you can make the shape change. So you dictate it. You dictate how fast you are changing the shape, how fast the sample is being sheared, shear rate. Let's assume for the moment you can afford to assume homogeneity, meaning that there's a single shear rate that describes the deformation everywhere in this layer of height, h. As I said, you can do the other way around by imposing a stress or force on the upper surface. Now I want you to appreciate that this is a very different scenario. That when you do that, applying for a black box, for something you don't know what it is, okay, a piece of sample that you, a material you just made, you want to learn about, for something that you have no clue, when you impose certain stress, you realize there's no way you would know at what speed the upper surface will attend. It's up to the material. So in that sense, you don't dictate, at least, you don't dictate how fast the material shears in a direct way. You only count on whatever the response will be. For example, for the same amount of force in between the sample, in between the two surfaces, if it's water, then of course you are going to achieve much higher speed than if it is honey. So that's just a different way of interrogating the material. We will come back many times regarding the different way to cause shape change. Okay, so I think with that I covered what is the basic starting point. I do want from the very beginning, since keep in mind, you know, folks, keep in mind the rheology anyone would have taken on polymer rheology per se, not even just rheology, polymer rheology. There's a question of how much the physics of the rheology is discussed, the polymer physics part. So I do want right away to impose or to make sure that you understand what I'm dealing with. I hate it when it does this. Okay, I just want to get this to this page. All I want you to keep in mind is the several hundred billion pounds of polymers. Typically, the way we deal with, there are hardly any solvent. It's just a neat melt. And in its, disordered state, above Tm, above Tg, it's really magnifying 1,000,000 times is really what you see is the spall of a crystal noodle. Really accurately can be viewed like so. And the part I invite you to appreciate is it's obviously highly complex. And in fact, complex to the point today we still don't know how to set up a correct analytical account about how this, I give you an example, even if you just have a a 10 micron by 10 micron by 10 micron piece of material, there will be something like 10 to the 10 chains already, typically. So it's just a mind-boggling, complicated system, right? There are that many chains, and they mingle with each other. They happily try to diffuse around. That's a bit of the polymer physics. And that is all actually captured in our first 2 chapters. Perhaps you can flip through for parts that is required. But for now, I just need you to know that there are chains like this, and each chain will diffuse around. When I use this kind of terms, diffusion, I mean, if you guys don't know what diffusion is, then I am a little bit impaired by my ability to teach. I mean, it's basically when you have a certain temperature, molecule will move around. In water, in benzene, the molecule moves extremely fast. Don't quote me, quote me, maybe in a nanosecond or much smaller than that, I think even. The water molecules probably move. I don't quote me because it's trivial to Google to find out. No need to. But then when you connect them into a polymer chain, it's the same deal. They may still move quite fast. But when the chains become very long and when your system is cooled close to so-called TG, in other words, when they start to freeze up, the best example of TG for you guys would be think about sugar. If you melt it into honey-like sugar, and if you can quench it fast enough to avoid crystallization, the way Chinese people make sculptures out of sugar, tangzhe so-called, then that's a glassy state, and you see why all of a sudden viscosity shoots up to infinity. So in any event, this is the object. All we all need to acknowledge it has ability to move around typically because we're dealing with it above Tm and Tg. And it becomes more difficult to move around as you approach the so-called glass transition temperature. And it becomes more difficult to move around if the chains are longer. For example, anytime you double the chain length, if the polymer is so-called entangled, which means long enough, then anytime you double the chain length, the speed with which it can move will slow down by a factor of 10. So this is, I mean, if we call that moving around is called relaxation time, tau, then that time typically goes with the chain length to the 3.4 power. I think this is enough information. Okay, you may say, oh, I'm curious why it's 3.4. Well, that's all explained in the first 2 chapters. So for those who need to go to details, we can get to there. For now, you can just acknowledge, just accept that knowledge. That's good enough. So a polymer is quite unique compared to other materials, and its most important parameter in the polymer science is chain length. The fact, you have ability to use different chain lengths in this example, see how much it has affected its property. And it turns out, again, so for the sake of argument, I mean, I know it's viscosity, for example, even. What is viscosity, right? It's basically according to what Newton worked out, Newtonian liquid, he found that the viscosity, remember last time I already told you what is the stress, shear stress. We usually don't write xy anymore because we know if we are talking about shear, then this is, oh God. I have to figure out how to, this does not help. Then, you don't need this label, just sigma. Then the Newtonian, Newton discovered that the force divided by the area, that's the stress. That stress is going to be proportional to shear rate, which in your experiment you already know is just V over H that you have control. As an experimentalist, you can just move your surface with certain velocity. You know how much it's from the lower surface, which is fixed, so you have shear rate. And Newton found out that the stress involved turns out to be linearly proportional to the shear rate, and this linearity is viscosity or shear viscosity. Right? So I'm just trying to further offer to you that our polymer I see it does all kinds of strange things. Our polymer is such that, again, describing book chapter 2, we don't need to get there. But basically, for our polymer that we're dealing with here, the viscosity will be proportional to the relaxation time. It also changes with molecular weight very strongly, 3.4 power. When the chain length is long enough, and that's something probably will not deal too much about. In other words, when the chain is sufficiently long, this behavior is obeyed. Oh gosh, that's a so yeah. Yeah, the contrast is the okay. So now you can see that this chain has the same issue. Oh gosh, I see I have the same issue here, where I casually defined a relaxation time tau. I just mean that this chain moved about the same distance as its own size, which in polymer rheology called radius of gyration, or the coil size. Okay, any chain has a size because any of the chain can be viewed as a Gaussian coil. Okay, so this is a way to for you to appreciate that the viscosity or relaxation time indeed can be very large because your polymer can be very long, the polymer chain. Questions, any? So you need to stop me if any part is something that that you need a little more information on. Okay, so I think this, of course, is the core part of the subject. That your object, which is this chain, right? There are of course many of them. Your object, which is this chain, has the ability to move around, and it moves around. As I repeating myself, it moves around depending on its chain length, and it turns out it also depending on the temperature. And for example, the temperature dependence of viscosity is such when the temperature approaches so-called glass transition temperature, the viscosity just diverges. Okay. So this is an aspect we will hardly need to deal with in this subject. We will typically be just sitting at some particular, sitting at some particular temperature and speak about the rest of the issues. In other words, if you sit at this temperature, you will have an issue of the corresponding relaxation times at this T1, let's say. We don't even normally, in this book, in this hardly ever address that issue. So just pick up a temperature where relevant for polymer processing. There will be a particular viscosity, there will be a particular relaxation time, and the reason I emphasize about this relaxation time is because we will quickly get to the bottom of issues such as whether this deformation field should always be expected to be linear or not. Okay, so so is that okay for me to introduce this much about what is the relaxation time? Just some characteristic time scale, as I mean, nothing need to be mathematical and sophisticated. So just a time for this chain, a moment later we'll move to here, okay? And that will take a time tau. That's it. Good enough. I mean, certainly that's what's happened. We know for certain. This is without any dispute. Yes? How do I define? I don't think I hear your question. How do I define? The end conformation. No, so that turns out I simplified the matter, but of course it's equivalent. There are two issues. He actually brought it up. In other words, when you have a chain, after tau, after a tau that we are concerned ourselves with, remember last time, yeah, so after tau, this conformation may be already somewhat different, okay, when you look like this now. Yeah. I'm going to avoid that problem by telling you the following. This chain, as I said, is a so-called Gaussian coil. It has a size, whatever is its size. The convenient thing that I know we can say and do and is that the time it takes for this chain to move a distance about its size, which is what I said, it turns out is a good way to define the time. So we can just use that as the time. So it turns out, I think you are quite right. In fact, I scratch my head all the time on that. In other words, how do you quantify after tau how much conformational change has happened? A short answer, noticeable amount. Yeah, the appreciable amount. Yeah. That's the same, right? So they are just 1/6. Yeah, yeah. So and then distance is no different in the sense, since we're on this page, they are typically proportional to the square root of the chain length. Yeah, yeah, yeah. Good clarification. Yeah. So here we are. But I hope I did not mislead you when I draw such a thing that they moved away. They moved away with such difficulty because all other chains are there too, in its own space. This is called entanglement. There's a careful discussion about it in chapter 2 through so-called packing model. I can even point out exactly around the packing model. That's on page 35. Basically, a chain, of course, occupies some so-called pervasive volume. But the one chain does not occupy it. You need many chains in that same space. Okay, so as the chain becomes longer, it turns out, it's all described there. As the chain becomes longer, in its own pervasive volume, there will be more chains. Okay. So this is why when the chain length is longer, there will be more chains in its own space. Imagine you are that chain. Okay, there will be many, many other chains in your own space. And that's very clouded. And that cloudedness is called entanglement. And this is the best way to capture that. Looks how they are in each other's way there. So in any event, I was just trying to say a few things that what we're dealing with, right? 24 books written on this. The objective, anything on polymer rheology, supposedly is to comprehend how this thing, not trillion. I mean, trillion is never the right word. I have to figure out what are those when it's 10 to the 12 or 10 to the 18 molecules. When there are so many chains there and they are all interfering with each other, at least in its neighboring space, it's a mess. And then you are trying to subject that to deformation, fast deformation. And I will say just a little bit more soon about what we mean by fast deformation. Basically, we are impatient. We want to produce 10,000 of such bottles in an hour instead of 10 of them. So we necessarily try to squeeze these guys very fast through shape-changing process. So let's get to the point. I wish the next 5 minutes are questions. I wish I were aware that they are not properly answered 30 years ago. If I knew, we would have started to work on it much earlier than we did. So no audio detected. What are you talking about? So I see I'm in some kind of trouble here because I think we are in a span mode that we don't want to be now. It doesn't allow me to turn. It's never happened when I last time teach this with the same software. So what is? I'm trying to get to the next page. You know, for the sake of argument. I was wondering last time I was using only PowerPoint or not. Let's for the sake of argument, let's switch to PowerPoint. We can always go back and forth, copy everything backward. Oops. Did you? I had less confidence in this because not every time I see my pen thing disappears again. Here we are. Okay. We're back. Okay. So now let's talk about something, a serious piece of business here. So suppose you do your shear, right? Your upper surface, you have a bottom surface, you have a height of h, okay? And all of a sudden you start to move the upper surface. So for example, if your upper surface all of a sudden at t equals 0, you start to move it. So if you look at your upper surface in terms of where it's moving, at some point it moved to x, and this x just increases linearly in time, which translates, because the slope is v, which translates to what we call a startup shear. That is to say, your velocity all of a sudden from 0, you jack it up and start to, I know I didn't draw well, you start to attain a finite speed. So I'm speaking about the same thing. And let's appreciate this a little further by asking, by pay attention to when it, let's say when it moves to also just one h on the top. That is when x is h. And ask yourself how much time it took you to move the upper surface 1h. Well, you know it because x is v times t, right? Yeah? And you are just asking a particular time when you have moved 1h to the right. Yeah? And that's a very special point because that's just about, if you like, that's x over h equals 1, right? In that limit. Let's call that x1. So that's a very special point. In terms of shape change, it changed substantially. How much? In fact, the sample basically tilted 45 degrees, right? It's like, so you moved, the sample is being sheared the same amount as its height, h. And you ask how long that has taken. I see some of you are losing me, look like. Is this not clear? So we're merely asking, since you are just start to have a startup shear, you start to deform your sample or shear your sample, or you cause a shape change of your sample, you take your time, you just start to move your upper surface at a prescribed speed, v, that you already chosen to use. And you travel until it reaches 1h, same as the height. And you ask yourself, gee, how long did that take? Well, you take t1, and that's what I gave you here, There's no sweat here. So what is that? That T1 is, of course, by definition, is H over V, right? I just flip this to the side, right? Okay? And what is that? That, of course, is what we learned as the reciprocal shear rate, right? Because shear rate was V over H. All this is pretty elementary because I can write it this way for you. X is V times T, okay? And then if I divide by H, oh Lord, I have all kinds of troubles here today. And I think I need to put this away, that's for sure. I divide the H on both sides. And this is, of course, on the left is, of course, the degree of shape change. That's the gamma, the shear strength, right? On the right, of course, it is shear rate times T. And if you want to get if you want to get it fancy, you can think about this as this, that, and then you can integrate, and of course that's that again. In the limit when gamma dot is a constant, right? So there are a million ways to do it. They're all the same things, completely trivial. And of course you can ask yourself, again, trivial, ask yourself, gee, what time it takes for me to achieve a strength of 100%. That's gamma 1 equals 1. And that's the same as looking at the formula here. That's gamma dot T equals 1. And that's T1 is 1 over gamma dot. And that's what I had. So it's just utterly trivial. The time it takes to make 100% deformation, we call this 100% deformation. I use this word a million times in the future. 100% deformation. The time it takes is the reciprocal of the shear rate, or more precisely, is H over V. Yeah. Completely straightforward. Yes. It's just it's embarrassingly simple. But what's next I'm about to say is not so recognizable in some way. In any case, I actually like to tease myself all the time. I knew, I learned rheology myself. No such a book as this one was around. I heard a rumor that when you shear a piece, when you deform a piece of material, you naturally introduce a time scale into the problem. And me, even though I'm not a chemical engineer, I'm a physicist, I still know, I know why you introduce a time scale, because if you flip the shear rate, it is a time scale. Meaning when I say flip, the reciprocal of shear rate is a time scale. So I'm truly aware that the reciprocal of shear rate is a time scale. But I never truly appreciated it is a very specific time scale, or rather, it specifically says it is the time to make 100% deformation it takes, right? I proved it. Okay, so this is all completely boring so far. I'm bored to death. But the next point is not. The next point, quickly. I mean, this is, of course, I'm not saying anything new so far. The next point is due to Weisenberg, for example, is you got the time, T1, what do you have this T1 for? Why you need to figure out what this T1 is? We, and of course, this is a tradition in chemical engineering and in other fields of I think chemical engineering is pretty typical field where people are looking for dimensionless numbers. The reason is actually quite profound, of course. In other words, you can never say that when you run pretty fast. That is totally meaningless. Even if you say you run as fast as, let's say 100 meter, you run in 15 seconds. Wow. Again, if I don't have any other information, I have no way of knowing 15 seconds is fast or not. Okay? The only way you know this man is faster than that man is you compare with the world record holders. Okay? He used 9.6 and you use 15. Well, that's very typical. The best human is almost twice as much as we can do. So this should give you a clue. I got one time, that's T1. For me to figure out whether this T1, which I do for processing, is fast or not, what do I need then? Huh? We need another time. A reference. We need another time. And what is the other time? Yeah, the tau. All this seems utterly simple. But the next point, utterly simple and be discussed for many decades. So here he helped me answer the question. So we have to flip a page by just doing that, right? Let me see. So here comes. Alex told me how to do it. So basically, I have a T1, but let me be gentle. Let me do it in a very heuristic way. This T1, he says we should compare with tau. And now you really ought to think. You really, as I said, 31 years ago, that if I realized this, I would be in a hurry, start to think about what is going on, what's the physics. Because you could have this T1. I give you the profound way, the striking way. What if this T1 is much shorter than tau? Okay, apple to apple, time to time, you can compare. What does it mean T1 is much shorter than tau? It means that within tau, I could have moved my upper plate many H's to the right. Many. Not funny, meaning so many. Easily they can be 100. By the way, why I say this is as old as many decades, is people have introduced this comparison long ago by the name of Weissenberg, a pioneer. Weissenberg, today we call it Weissenberg number. He recognized this apple-to-apple comparison is pretty important. Weissenberg number. I'm sure you heard about Weissenberg number, but I don't know to what degree it was introduced in this manner. That That, of course, we know it when this number is very large, we know something is being deformed fast. But concretely, we are talking about fast in the sense within tau, I will move, where Wenzberger number is 100 means I will move 100 h to the right. And think about this guy that has a particular tau involved for this complicated object. And you are forcing, so, let the tau be 1 second. I don't know what number you feel comfortable doing. Basically, it has a time tau, let's say it's 10 seconds. But it turns out within that, so within 10 seconds, if you give it 10 seconds, the chain will happily move, right? From its size of here to its size here, right? That's what I define, what is a tau. So they happily would move if you give them 10 seconds. Now, within that 10 seconds, you actually shear the material. You shear it in such a way that it would be the shape change or whatever. It's sheared in such a way that if you have a height of h, or I know we don't need to talk about find it. So suppose this chain is being grabbed on and being sheared. So this is your shear. Imagine this chain. And of course, the way we define it. Yes, I better just switch back to my other file here. So for the simple argument, basically I'm force this molecule to move while keeping this bottom fixed. Just imagine somehow I'm moved. This has a size of Rg, and try to move it within tau 100 times to the right. And keep in mind, this is not a single chain, right? The other chains are mingled there. All the chains are in here. What a mess. What will happen? What will happen is what we will try to address throughout this course. We'll take several steps to do this. But I just want to intrigue you with this condition. I don't think you will be able to appreciate this enough without me. So let's see, I know we are flipping to a different thing. I know. Now you see, now it works, it writes again. So let's say introduction. I have this definition of rheology, and our second page should be let's just face it. Our second point could be just Weissenberg numbers or something about a measure of how fast we are doing deformation, right? So from that we had a definition of Weissenberg number like this. The third topic, this is not strictly following the book. It's just a way for me to bring you up to speed with so that we can eventually start to tackle the core part of the rheology, which start on page chapter 6. So we can call that a fine deformation. We have said nothing about it, but it will be impossible not to discuss it. So a fine deformation, if anyone take a rheology course that has an element of trying to connect the molecular world versus the microscopic world, the 6th order magnitude gap, then one almost necessarily have to introduce this concept of a fine deformation. A fine deformation is what I was already trying to do here, is the molecular or microscopic deformation. Deformation that occur on microscopic scales. The molecular deformation follows the microscopically imposed deformation. Imposed deformation. So if you have a piece of sample that you're shearing, right, simple shear, on microscopic scales, just for your information, this height typically is on the order of 1 millimeter. That's microscopic. Then it turns out we claim, or we define a fine deformation. When that fine deformation holds, it means that we can visualize that this chain is also suffering the same shear deformation. The characteristics of shear is its displacement horizontally is proportional to where they are from the bottom. And the proportionality constant is, of course, a measure of the shape change, gamma. So basically, a fine deformation just I know I'm trying to, not going to be easy, trying to draw a change. It means that my initial point is here, now it is here, if I'm shearing that way. And how much that shear depends on how far you're from the bottom. So it's just a trivial matter. The shape change microscopically is also happening. That shape change is also happening molecularly at the molecular scale. That's what a fine deformation means. Of course, you'll ask, what on earth? Why this is possible? Why you could have a fine deformation? Why the molecule also tilts? And shear is always more difficult to discuss. You should never mind about the shear. Extension, right? The only reason I didn't do it is I haven't described in more detail about how to describe extension yet. A basic extension, you can be my guest, just hold one side, so later it will become elongated to here now. A fine deformation, again, means your molecule initially was coiled, and then later finally become more cigar-like because it's elongated to the same degree. And that's called a fine deformation. It's very, very straightforward, but very essential concept. The question you need to ask is why the molecule can do that. Or what even allowed you to have this notion discussed that the fine deformation occurs? Well, we like to say that the whole polymer science and certainly the polymer physics part was built on our understanding on rubber, how we describe rubber in terms of deformation again. There is where we can really start to convince ourselves that a fine deformation is good. So I'm drawing a cross-linked rubber. This is a classical way to describe or to motivate where a fine deformation comes from. Okay? Cross-linked rubber, you can do it in different ways. You could have a pre-made melt, and then you start to introduce peroxide or whatever cross-linking mechanism you have, and you then start to fix them. And abstractly, one can denote them as I just draw. Now, your whole sample is a giant single molecule because everywhere is chemically connected. And of course, this is 3D. I could only draw 2D for you. So in any case, if you have cross-linking, then the pioneers in the field have immediately suggested when you stretch your cross-linked rubber, you can apply a fine deformation because you have cross-links. I'm not drawing the rest, but basically you can see that it becomes elongated, right? If this is a 2L of some unit, let's call it LC, and this LC is 0, now the 2LC is this long now. So you have a stretching ratio of LC over LC 0, which is about, what did I do? Maybe 2? Something like that, right? You doubled your length. When you double the length of your sample, it turns out the separation between the cross-link points also doubled. And that's a very acceptable way to propose that you have a fine deformation, okay? So that's how where a fine deformation started. Now, the real world is never that simple. In particular, much of our polymer need to be processed. Even the rubber need to be processed before you cross-link it. Because if you cross-link it, it will never be able to adapt to a different shape freely anymore. So we're talking about uncross-linked sample system, right? So no cross-linking now. Imagine we have no cross-linking anymore. Well, here comes the magic of the tau, right? We talk about relaxation time tau enough times. As long I claim, this is what you need to follow me now. As long, so all of a sudden, let's say, all of a sudden you start to shear it, just for the sake of argument. Extension is the same, but let's say all of a sudden you start to shear it, right? As I told you, the velocity, all of a sudden you apply a certain speed on top. Let's say your tau is here on that scale of starting from 0. Then, of course, as long as your t, as long as you are still far from tau, what happens? You know that. Well, as long as that is the case, the molecule hasn't moved much, for sure. Meanwhile, the molecules are all constrained by the fact there are other chains around it. Okay, so I draw something very casually here, and in fact, to do it more accurately, is for me to at least use a different color. So that's a black chain, and then the green chain is another chain. They constrain each other because they cannot cross. We're far from the condition where the chain will break. So in that limit, you can see that this acts similarly like a cross-link. I mean, it is, believe it or not, it turns out to be a reasonable thing to say and do. That these chains, when there are so many of the same chain in its space, the fact they cannot cross each other when you stretch is the same as if this uncrossability acts like a crosslink. Okay, so it looks like a crosslink. Then I recover the condition where I can speak about affine deformation. I hope you are with me with the logic, right? We speak about affine deformation first because you have a permanent crosslink network, then you can speak about it. So that's the permanent crosslink network through vulcanization of your rubber and whatnot. But now we're talking about a melt that has no cross-linking, but as long as, or untangled melt to be precise, in the sense the chains are rather long, beyond certain chain lengths. As long as you are in this condition, then I can apply the logic I just spoke about for cross-link system, because in that limit, I just claim that the uncrossability act the same as cross-linking. Then I'm as if I was dealing with a cross-linked system, and therefore it should be okay for affine deformation to hold as a approximate way to describe the response of my melt to external deformation. So I think this is pretty straightforward to assert. And there comes the punchline, or if you like, the whole 9 yard. Okay, the whole subject that this book is devoted to, the whole subject that this book is devoted to is about answering the following 2 questions. And these 2 questions, in my opinion, were not properly treated previously. First question, very much related to what just said. You may say, what enabled affine deformation? There are many ways to phrase it. I can be very casual here. Why why affine deformation is possible? Affine deformation is possible. Or what causes you to have affine deformation? So you can have many different versions. Okay, I can verbally say many ways. It's the same. In other words, how come there is affine deformation? Which, of course, I have already answered in the last 3 minutes. Yeah, by the fact of that you have uncrossability when the chains are very long and it acts like a crosslink. Yes. That's exactly something I have yet to answer for you. So I said if it's much less than tau, if t equals 0 is when I start to examine my system, then within very short times of tau, perhaps this affine deformation still holds. Yeah. So right, that makes sense. So the next question is exactly when affine deformation ceases, or ceases rather. These are the only questions. In other words, I can reduce everything we need to study to these two questions. If we have a proper understanding of why, you see, the problem is if you don't start to describe what makes a fine deformation possible, there's no way to answer when it stops. So, okay, and I can be explicit about it. The tube model, which we will comment on many times in the future, which is the prevailing leading theoretical framework for understanding nonlinear polymer rheology, particularly entangled polymer rheology, which is all where the challenge is. Essentially, I don't think my opponent could anyone who object me could really object that it does not explain. Let's be very I guess explain is the right word. Basically, the tube model is treating this first problem in a way it doesn't try to directly answer it. Does not explain where a fine deformation comes from. It actually assumes so. It assumes there is a fine deformation, but it doesn't explain what it originates from. I mean, what could enable you to have it. I try to be as soft as possible. I think the recording is good for me to stay within my boundaries and not go overboard on this parallel universe that we're talking about. Okay. So if you like to think that what enabled a fine deformation has to do with uncrossability, which produce what's called entanglement. If you think entanglement means what I try to depict it here, then the second question really is asking, as Alex was trying to ask, is really asking, when can I anticipate disentanglement? Or rather, that was the question. So I can give you a short answer. A long answer take a whole book to talk about. For example, in fact, this concept goes a little broader than that. For example, I think everyone agreed when we are looking at our object for time scale much shorter than tau, it's going to be a fine. And of course, by the time you are here, near tau, it's hard for you to argue that there is still a fineness here because chain would have moved around, right? It would not have a chance to grab onto each other. So this gives me an opportunity to generalize the concept of disentanglement. Let me talk about this general concept, this more less interesting limit first. I can claim. So we talked about disentanglement, and we talk. But by the way, I raised these two questions with the following things in mind, which is of course under deformation something, right? Something under deformation, which is What if this is being deformed fast? I mean, nothing is interesting if you don't address this limit, yeah? Because that's the limit where we want to be able to understand so that we can process our material fast, right? Nobody can afford to go to the limit when Wi is smaller than 1. That's pretty clear. So by necessity, the task or the mission of rheology is in dealing with understanding the rheology in this limit. And in that limit, we'll soon, we say this all the time, we'll soon find out that's the nonlinear limit, the nonlinear response limit. I want to just for a moment come back to, and careful what I did. We had this in mind, fast deformation, and we are asking, under that case, when disentanglement occurs, which addresses the second question. I just want you to realize that that even under this condition, I can broaden the meaning, or I can broaden the scope of our investigation, and also ask, do you have disentanglement? Well, you do. When you in that limit, you're shearing very slowly. By the time you make 100% deformation, you have taken a time of tau. It voluntarily disentangles. Yeah? Yes? Good point, good point. So this gives me a chance to say something. Yeah, good point. So the way we today know how to treat, nobody else knows anything differently, this is a mess. It involves 10 to the whatever. Even in its neighbor, there will be, let's say, 100 chains around me. And we don't have any theoretical tools to simultaneously deal with all these 100 chains, how they are interacting with each other, or interfering with each other, or untangling with each other. So a typical way, even the best physicists can do no better, is to take a test chain. In other words, just give me any of the chains and ask myself, can I describe this chosen chain in terms of trying to capturing what other chains are doing to me? So so this is called mean field approach. We are going to take a test chain. We're going to do the best we can to capture the essence of the presence of other chain in terms of its effect on me. If I could capture that, then at least I will have a theory. Because it's a test chain, which means I speak about every chain. That's the idea. Yeah, by definition. The test chain is any chain, indiscriminatively. So we are only in the limit, not the real world you guys dealing with. In all the theoretical treatment, typically, and we are still not there. We just assume all chain lengths are the same. Then I can convince you any chain is the same chain, right? No chains are of different lengths, which of course is not reality, but as a first approximation is good enough. So so that your question really speaks about the whole methodology about how to treat such a complex problem. And the whole deal it's fascinating. So as I said, the problem is not treatable. The only way you can do is pick up a chain and try to account for the presence of other chains. And that approach is necessarily going to be approximate. In the following sense, when I use the word approximate. Approximate in the sense you're going to make approximations. Okay? When you make approximation, you better be nervous. In other words, you're going to throw away some things and keep something more important. What I'm talking about something very generic here. When you do so, the only way you can be sure you're doing something proper, reliable, is if you already have the right picture, the right guess, the right intuition about what is governing the physics here, so that you know what you can throw away, what you cannot. This becomes highly philosophical. So if you don't, then you cannot be so certain that you have made the right approximation. Okay, well, if any lesson when the problem is so complicated, is perhaps we can ask experiment to inform us as much as possible about what could be the right approximation to make. I see I'm out of time, actually. So this is a good point to stop. Yeah, so I do want to hit home right away so that you can see how it eventually evolves. Okay, any other questions? All right, so we will resume next week.